Scientific notation is a way of expressing numbers that are too big or too small to be conveniently written in decimal form. It is commonly used by scientists, mathematicians and engineers. On scientific calculators it is known as Sci display mode. In scientific notation all numbers are written in the form m times 10n, where the exponent n is an integer, and the coefficient m is any real number, called the significand or mantissa. The term mantissa may cause confusion, however, because it can also refer to the fractional part of the common logarithm. If the number is negative, then a minus sign precedes m. Decimal floating point is a computer arithmetic system closely related to scientific notation. Normalized notation. Any given integer can be written in the form m times 10 caret n in many ways. For example, 350 can be written as 7002350000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 35 times 101 or 700235000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 The exponent n is chosen so that the absolute value of m remains at least 1 but less than 10. Thus 350 is written as 7002350000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000s as the exponent n gives the number's order of magnitude. In normalized notation, the exponent n is negative for a number with absolute value between 0 and 1. The 10 and exponent are often omitted when the exponent is 0. Normalized scientific form is the typical form of expression of large numbers in many fields, unless an unnormalized form, such as engineering notation, is desired. Normalized scientific notation is often called exponential notation, although the latter term is more general and also applies when m is not restricted to the range 1 to 10 and to bases other than 10. Engineering notation. Engineering notation differs from normalized scientific notation in that the exponent n is restricted to multiples of 3. Consequently, the absolute value of m is in the range 1 m less than 1000, rather than 1 m less than 10. Though similar in concept, engineering notation is rarely called scientific notation. Engineering notation allows the numbers to explicitly match their corresponding SI prefixes, which facilitates reading and oral communication. For example, 69921250000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000w 12.5 nanometers, and written as 6992125000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 times 10⁻8 meters would likely be read out as 1.25 times 10 to the negative 8 meters. Significant figures. A significant figure is a digit in a number that adds to its precision. This includes all non-zero numbers, zeros between significant digits, and zeros indicated to be significant. Leading and trailing zeros are not significant because they exist only to show the scale of the number. Therefore, 1,230,400 usually has 5 significant figures. 1, 2, 3, 0, and 4. The final 2 zeros serve only as placeholders and add no precision to the original number. When a number is converted into normalized scientific notation, it is scaled down to a number between 1 and 10. All of the significant digits remain, but the place-holding zeros are no longer required. Thus 1,230,400 would become 1.2304 times 106. However, there is also the possibility that the number may be known to 6 or more significant figures. in which case the number would be shown as 1.23040 times 106. Thus, an additional advantage of scientific notation is that the number of significant figures is clearer. Estimated final digit. It is customary in scientific measurements to record all the definitely known digits from the measurements, and to estimate at least one additional digit if there is any information at all available to enable the observer to make an estimate. The resulting number contains more information than it would without that extra digit, and it may be considered a significant digit because it conveys some information leading to greater precision in measurements and in aggregations of measurements. Additional information about precision can be conveyed through additional notations. It is often useful to know how exact the final digits are. For instance, the accepted value of the unit of elementary charge can properly be expressed as 6981160217648699991.602176487 times 10⁻19c, which is shorthand for 6981160217648699999 times 10⁻19c notation. Most calculators and many computer programs present very large and very small results in scientific notation, typically invoked by a key labeled exp, eex, ex, or e depending on vendor and model. Because superscripted exponents like 107 cannot always be conveniently displayed, the letter e or e is often used to represent times 10 raised to the power of, and is followed by the value of the exponent. In other words, for any two real numbers m and n, the usage of n would indicate a value of m times 10n. In this usage, the character e is not related to the mathematical constant e or the exponential function x, and though it stands for exponent, the notation is usually referred to as e notation or e notation, rather than exponential notation. The use of this notation is not encouraged in publications. Examples and other notations in most popular programming languages: 6.022 times 10 to the 23 or 6.022 times 10 to the 23 is equivalent to 702360220000000000000 6.022 times 1023 and 6965160000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 would be written in 1.6 times 10 to the minus 35. Fortran also uses d to signify double precision numbers. The ALGOL 60 programming language uses a subscript 10 character instead of the letter e. For example, 6.02214151023. The ALGOL 68 programming language has the choice of 4 characters, e, or 10. By examples: 6.0221415 times 10 to the 23, 6.0221415 times 10 to the 23, 6.0221415 23 or 6.02214151023. Decimal exponent symbol is part of the Unicode standard, e.g., 6.022141523. It is included as U+23E8 decimal exponent symbol to accommodate usage in the programming languages ALGOL 60 and ALGOL 68. The T83 series and T84 Plus series of calculators use a stylized E character to display decimal exponent and the 10 character to denote an equivalent times 10 caret operator. The similar programming language requires the use of an, for example, 6.0221415 and 23, order of magnitude. Scientific notation also enables simpler order of magnitude comparisons. A proton's mass is 0.00000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 kilogram. If written as 6973167260000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 with that of an electron, given below. The order of magnitude of that of an electron, given below. The order of magnitude of the ratio of the masses can be obtained by comparing the exponents instead of the more error-prone task of counting the leading zeros. In this case, -27 is larger than -31 and therefore the proton is roughly 4 orders of magnitude more massive than the electron. Scientific notation also avoids misunderstandings due to regional differences in certain quantifiers, such as billion, which might indicate either 109 or 1012. In physics and astrophysics, the number of orders of magnitude between two numbers is sometimes referred to as dex, a contraction of decimal exponent. For instance, if two numbers are within 1 dex of each other, then the ratio of the larger to the smaller number is less than 10. Fractional values can be used, so if within 0.5 dex, the ratio is less than, and so on. Use of spaces. In normalized scientific notation, in E notation, and in engineering notation, the space that is allowed only before and after times, or in front of E or E, is sometimes omitted, though it is less common to do so before the alphabetical character. Further examples of scientific notation. An electron's mass is about 0.000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 times 10⁻31 kilogram. In scientific notation, this is written 702459736000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 The Earth's circumference is approximately 40 million meters. In scientific notation, this is 70074 times 107 meters. In engineering notation, this is written 70074 times 106 meters. In SI writing style, this may be written 70074 megameters. An inch is defined as exactly 25.4 millimeters. Quoting a value of 25.400 millimeters shows that the value is correct to the nearest micrometer. An approximated value with only 3 significant digits would be 699825400000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 instead. As there is no limit to the number of significant digits, the length of an inch could, if required, be written as 699825400000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 millimeters instead. Converting numbers. Converting a number in these cases means to either convert the number into scientific notation form, convert it back into decimal form, or to change the exponent part of the equation. None of these alter the actual number, only how it's expressed. Decimal to scientific. First, move the decimal separator point the required amount, n, to make the number's value within a desired range, between 1 and 10 for normalized notation. If the decimal was moved to the left, append times 10n, to the right, times 10n, to represent the number 1,230,400 in normalized scientific notation. The decimal separator would be moved 6 digits to the left and times 106 appended, resulting in 70061230400000001.2304 times 106. The number minus 0.00403321 would have its decimal separator shifted 3 digits to the right instead of the left and yield 30025967900000000 minus 4.0321 times 10 minus 3. As a result, scientific to decimal converting a number from scientific notation to decimal notation, first remove the times 10n on the end, then shift the decimal separator n digits to the right or left. The number 70061230400000001.2304 times 106 would have its decimal separator shifted 6 digits to the right and become 1,230,400, while 30025967900000000 minus 4.0321 times 10 minus 3 would have its decimal separator moved 3 digits to the left and be minus 0.00403321. Exponential conversion between different scientific notation representations of the same number with different exponential values is achieved by performing opposite operations of multiplication or division by a power of 10 on the significand and subtraction or addition of 1 on the exponent part. The decimal separator in the significand is shifted x places to the left and 1x is added to the exponent, as shown below. 700312340000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 12.34 times 102 equals 7003123400000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 123.4 times 101 equals 1234. Basic operations. Give on two numbers in scientific notation, and multiplication and division are performed using the rules for operation with exponentiation, and some examples are, and addition and subtraction require the numbers to be represented using the same exponential part, so that the significand can be simply added or subtracted. With next, add or subtract the significands. An example. Other bases. While base 10 is normally used for scientific notation, powers of other bases can be used too, base 2 being the next most commonly used one. For example, in base 2 scientific notation, the number 1001b in binary is written as 1.001b times 2d11b or 1.001b times 10b11b using binary numbers. In E notation, this is written as 1.001b11b with the letter E now standing for times 2 to the power here, in order to better distinguish this base 2 exponent from a base 10 exponent. A base 2 exponent is sometimes also indicated by using the letter B instead of E. A shorthand notation originally proposed by Bruce Allen Martin of Brookhaven National Laboratory in 1968, as in 1.001b b11b. For comparison, the same number in decimal representation, 1.125 times 23, or 1.125b3. Some calculators use a mixed representation for binary floating point numbers, where the exponent is displayed as decimal number even in binary mode. So the above becomes 1.001b times 10b3d or shorter 1.001b3. This is closely related to the base 2 floating point representation commonly used in computer arithmetic, and the usage of IEC binary prefixes. Similar to B, the letters H and O are sometimes also used to indicate times 16 or 8 to the power, as in 1.25 equals 1.40h times 10h0h equals 1.40h0 equals 1.40h0, or 98,000 equals 2.77320 times 10,050 equals 2.77320 equals 2.7732 C5. Another similar convention to denote base 2 exponents is using a letter P. In this notation, the mantissa is always meant to be hexadecimal, whereas the exponent is always meant to be decimal. This notation can be produced by implementations of the print family of functions following the C99 specification and IEEE STD 1003.1 POSIX standard. When using the %A or %A conversion specifiers, it is also required by the IEEE 754-2008 binary floating point standard. Example: 1.3 det 42 represents 1.3d times 242. Engineering notation can be viewed as base 1000 scientific notation.